Hey everyone, and welcome back to a video with Miss Chemistry. And if this video helped you with your revision, please like and subscribe and comment down below. So we're going to do KP today, which is about gaseous equilibria, basically meaning that all of the entire mixture, all of the states are in a gaseous state. So all of the states are in a gaseous state. So it's the whole equation is in a gaseous state. So the total pressure is equal to the sum of all of the partial pressures inside this mixture of gases. That's what the total pressure is equal to. And the partial pressure is equal to the mole fraction of whatever gas you're calculating times by the total pressure of the whole entire mixture of the gas. And then the mole fraction is equal to the number of moles of the gas you're calculating divided by the total number of moles inside of the gas mixture. And then the sum of partial pressures can also be equal to 1 if necessary. So when we're writing the expression for Kp, for example, we have this equation. So if you know how to write your expressions for Kc, which is the equilibrium for concentration, then you would know how to do Kp, but it's a bit different. Instead, we do a P, we put a P, and we don't do square brackets. No square brackets for Kp, only square brackets for Kc. So this is how you'd write the expression. So you write your products over your reactants, and then it'll be in brackets, no square brackets, just brackets, and then we write a big P in because to show the partial pressure in the beginning of like whatever compound it is. Okay, so the effect of pressure of equilibrium of Kp. So Kp would have no effect. Kp would stay constant. And in this equation, for example, okay, what can we see here that I highlighted in red is the number of moles. Now we can see there's more moles on the right hand side than on the left hand side. There's more moles on the left hand side than the right hand side. My bad. So therefore, if pressure increases, the equilibrium will move to the side with fewer moles. Therefore, equilibria will move to the right hand side because there's only 2 moles on the right hand side, whereas there's 4 moles on the left hand side. And if you write the expression for this Kp, which is this, then since the pressure is increasing and it's moving and equilibrium moves to the right hand side, then the products increases and the reactants decreases until original Kp is restored. So if you understand that since pressure is increasing, it's moving to the right hand side, the side with fewer moles, more products are going to be made. It increases the number of products, whereas the left hand side, no pressure is on that side, so like the reactants decreases. And then in another example here, so I can see that there's 2 moles on the right hand side and there's 2 moles on the left hand side. So does it affect Kp? No. It has no effect on Kp. Kp still stays constant. And as the pressure and if pressure increases or decreases even, there's no effect on the equilibrium because there's the same number of moles on both sides, so it cancels out. So no effect on equilibrium, even if pressure increases or decreases, same number of moles. And Kp is not affected by pressure, the catalyst, or the concentration. It's only affected by temperature. Now, speaking of temperature, the effect of temperature of the equilibrium of Kp. Now, as I said, Kp is only affected by temperature. Therefore, Kp can increase or decrease depending on what the situation is. So, for example, in this equation, here, it's going exothermic in the forward direction, okay? Therefore, since it's going exothermic in the forward direction, that means temperature is increasing because when you increase the temperature, more heat is being released, and that's what exothermic is. So it's exothermic in the forward direction. Therefore, as the temperature increases, equilibrium moves to oppose the change by decreasing the pressure. So equilibrium would move to this side, okay? Because temperature increases and equilibrium moves to decrease the temperature, so it moves that way because it's exothermic in the forward direction. So equilibrium moves to the left hand side. And this is because equilibrium is exothermic in the forwards direction, so equilibrium moves to the left-hand side. So therefore Kp decreases because less products are being made because it's moving in the to this direction. And more reactants are made. So now let's get on to some exam questions, and I'm going to show you what you need to know for that A star. Okay, let's say in the exam question, this is from an exam question by the way, and they give us this equation. So 2 moles of sulfur trioxide into 2 moles of sulfur dioxide plus oxygen, and then they give us the Kp value for that equilibria for that equation. And then they give us another equation, which is 1 mole of sulfur trioxide into 1 mole of sulfur dioxide plus half a mole of oxygen. And it says calculate the value of Kp and reduce the units of Kp. Now, what I notice here is that you can see there's 2 moles of this, there's 2 moles of that, and there's 1 mole of oxygen. Right? So what I can say is that in order for 1 to get to a half, you need to divide by 2. You see? So basically they just divided by 2 for this whole thing. So in order to calculate a value of Kp, if it's something like this, you have to do square root of the Kp value, which is 7.62 times 10 to the power of 5. So this would be equal to 872.9261 ... And they usually want it in standard form, 3 significant figures. So it would be 8.73 times 10 to the power of 2. And then that's your value of Kp. And then deduce the units of Kp. So if you write the Kp expression for this equation, it would be the partial pressure of oxygen times by half times by the partial pressure of sulfur dioxide over the partial pressure of sulfur trioxide. And then this is going to be same as, so it could give us in kilopascal or pascal. I'm just going to use pascals. So this would be pascals to a half times pascal and pascals there. So a half times 1 would just be pascals. Oh yeah, pascals 3 over 2 because you add the indices because it's pascals 1. And then this is pascal over 1, and then when you divide it, you are subtracting the indices, so it will be pascals to the power of a half. So that's your units. Okay, so here's another question I got from an exam paper. So they give us this equation, 1 mole of carbon monoxide plus 2 moles of hydrogen gas to 1 mole of methanol. And the value for Kp they give it to us is 1.15 times 10 to the power minus 6. And then they give us this equation, 1 mole of methanol into 1 mole of carbon monoxide plus 2 moles of hydrogen. And it says calculate the value of Kp and deduce the units of Kp. Now, what I noticed from this equation and this equation is that this equation here is just the reverse of this equation. So it's just flipped, basically. So to calculate that, you do 1 over the value of Kp, which is here 1.15 times 10 to the power minus 6. And that equals like 869,565 point blah 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 blah. I mean 0.2174 da, 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 da. And we want it in standard form to 3 significant figures, so it'll be 8.70 times 10 to the power 5. And that's our value of Kp. So remember, reverse 1 over. kp. Reverse 1 over kp. Halving is square root because remember square root x is equal to like x of half anyway. So halving the equation means square root the kp. Reverse 1 over the kp. And to deduce the units for kp, so let's write our expression for this equation. So partial pressure for hydrogen, and then partial pressure for carbon monoxide over partial pressure of methanol. So if it's in kilopascal, because it says in the equation here kilopascal. So this, okay, basically you can just cancel out these kilopascals, and then the units is kilopascal squared. Okay, so let's have a go with these exam questions. So sulfur dioxide and oxygen were mixed in a 2:1 mole ratio and sealed and flasked with the catalyst. Okay, so you can see here that this reaction is exothermic because it's negative. This is T1. The partial pressure of sulfur dioxide in equilibrium was 24 kilopascal, and the total pressure in the flask was 104. Deduce the partial pressure of oxygen and hence calculate the mole fraction. Okay, so we can see here that sulfur dioxide and oxygen are in a 2:1 mole ratio. So I'll do 2:1 mole ratio here. And since the partial pressure of sulfur dioxide was 24, so 24, 224 you times by 12, so therefore the partial pressure of oxygen would be 12 kilopascal. And then the mole fraction of oxygen, so that's the number of moles of oxygen divided by the total number of moles. But we don't have the number of moles here, so we can use the equation. So the partial pressure is equal to the number of, is equal to the mole fraction times by the total pressure. And here we have the total pressure, which is 104 kilopascal. So the partial pressure over the total pressure equals the mole fraction, which is of oxygen. So what we do is we do 12 divided by 104, which gives us 0.115. I'll put to 3 decimal places, and then calculate the partial pressure of sulfur trioxide. So then we have the partial pressure of oxygen and the partial pressure of sulfur dioxide, but I want sulfur trioxide. So since the total pressure is 104, we can just minus the 12 plus 24 to find the partial pressure of sulfur trioxide. So that would be 68 kilopascal. Okay, write an expression for the equilibrium constant Kp for this reaction. Okay, easy enough. Easy 1 mark. So we do the partial pressure of sulfur trioxide squared, no square brackets, over squared partial pressure of oxygen. Okay, calculation for this. So now we can calculate Kp. So we know our sulfur trioxide is 68 kilopascal over 24 squared times by 12. And this gives us 0.66898 whatever. So that would be 0. If you're rounding to 3 decimal places, 0.669. And the unit would be, so you can see here that these squared things, they cancel out. So it'll be 1 over a kilopascal, and that would be kilopascal 12 minus 1. Okay. When equilibrium was established at a different temperature, T2, the value of Kp was found to have increased. So that means the number of products have been increasing. State which of T1 and T2 is the lower temperature and explain your answer. Okay. So T2 has Kp increased. Okay, so let's look here. Right. So it says to me, like I said at the beginning, that this equation is this whole reaction is exothermic. So that means temperature is increasing. So if the full reaction is exothermic, that means the equilibrium would move to oppose this increase in temperature. So it would move that way to create more reactants. Therefore, Kp does not increase. Therefore, it must be T2 that has the lower temperature because it increases Kp. So we're going to write T2. Explanation. I'm going to mention that it's exothermic. So equilibrium moves to the right hand side to oppose the decrease in temperature. Because if it's exothermic, but it produces more Kp, so more products of Kp, that means equilibrium moves to the right hand side to oppose the decrease in temperature because the temperature is beginning to decrease. Okay, and then in a further experiment, the amounts of sulfur dioxide and oxygen used, the catalyst and the temperature were all unchanged, while a flask of smaller volume was used. Deduce the effect on the yield. Okay, so obviously Kp is not affected by volume, so no effect. And effect on the yield of sulfur trioxide. So the yield would increase because if it's in a smaller volume, so let's say we have a big volume here and the reaction is going on. So this is the products and this is our reactants, and that's making our products. But if it's in a smaller volume here, so like this, then obviously it'll be more faster to make the product, so more products will be increasing because look how short that arrow is, bro. It's more faster, increases more of the products, and so therefore increases the yield of sulfur trioxide.